Okay, so hello everyone and welcome. My name is Yael Shadmi, and I'm very happy to welcome you to this Aspen Center for Physics lecture by Peter Onyisi from the University of Texas at Austin. So thanks for joining us here on Zoom. Please remember to mute your audio. We will have time for questions following the lecture. If you want to ask a question, please use the raise a hand button and I'll call on you. You can also type your questions into the chat and we'll read them out. I'm a physics professor at the Technion in Israel, and like many other people from around the world, I come here to the Aspen Center for Physics as often as I can, and often every summer. It's a long trip and the jet lag can be very bad, so why do this? Well, quite literally, the Aspen Center for Physics is like a physicist heaven on earth. Every summer, every normal summer, with no pandemic, that is, we have about roughly 500 leading physicists come here to attend several workshops. Each workshop is focused on a specific topic and lasts around 4 weeks. This summer, we're still here, but due to the pandemic, it's about half of this number. So what do we do here? We mainly talk to each other. We hear about new ideas. We tell others about our half-baked ideas and new ideas, and we think together. And I don't know what it is exactly, but there is some combination of an amazing group of researchers, both junior people just after their PhD and senior people who are all interested in similar questions. And then there's the mountains and the aspen trees and the music from the tent as the backdrop. And it all blends to create some sort of magic. And very often, these few weeks at Aspen fling us in completely new directions and fuel our research for a very long time. So I can tell you that quite a few places around the world are trying to emulate this model, and some of them are doing a great job, but this special Aspen magic is somehow very hard to replicate. And indeed, the impact that the center has had on advancing research in physics is truly amazing. One other thing that we do here, which is really important to us, is to try to share our joy of doing science with the community, that is, with you. So during normal years, we have Wednesday afternoons with kids, with fun lectures and demos and hamburgers. And of course, we have these public lectures, usually here on campus on Thursdays at 5:30. These days, we're doing this on Zoom, but we hope to see you again in person next year. These lectures are named after Heinz Pagels, who was a professor of physics at Rockefeller University. Among other things, Pagels was president of the New York Academy of Sciences, a member of the Aspen Center for Physics for 20 years, and president of the International League for Human Rights. He was a part-time local resident, and he died in a climbing accident in 1988. Pagels deeply cared about disseminating scientific knowledge to the public, and his family and friends instituted this lecture series in his honor. So when the pandemic hit last year, the first thing we decided to keep going was this public lecture series. We really hope to see you next year in person, but this is what we have for now. We have a very exciting blend of topics and great speakers this year. Next week, we will have Catherine Fries. She'll talk about the cosmic cocktail, 3 parts dark matter. And today, Peter Onyisi will tell us about the flavors of particle physics. Peter is an associate professor at the University of Texas at Austin. He got his PhD from Cornell and held a Fermi postdoctoral research fellowship at the University of Chicago before coming to Austin. He studies the fundamental interactions and building blocks of nature. And one thing that's very special about his research is that he has worked on very diverse experiments, starting with the Clio experiment at Cornell, which looked at mesons at relatively low energies. And these days, he does experiments at the Atlas detector, which is one of the main detectors looking at particle collisions at the CERN Large Hadron Collider. This detector is nothing short of amazing. It's probably one of the most complex machines ever built by humanity, and Peter is using it to explore the frontiers of our understanding of fundamental physics. So with this, I'm gonna turn the floor to Peter. please, Peter.
All right, thank you very much, Yael, for the introduction. So I'm very excited to be able to give this lecture and to be here in Aspen. It's been, even if we can't be here as many of us as we'd like in a normal year, we're still trying to carry on the magic. So let me go ahead and share on my screen here. And it's all up. Yeah, okay. All right. So I'm going to talk about the flavors of particle physics, and hopefully by the end of this, you'll know what that means. And you also notice that next week's lecture is about the cosmic cocktail. So you see we have inability to keep away from food and drink themed metaphors when talking about what we do in particle physics. So let me give you a little bit of a picture of where we are going to be going in this little chat. So this talk is really about matter. So when we talk about what we do as particle physicists, we look at matter and the way matter interacts with stuff, the forces that attract or repel things. So I'm only going to focus on the matter part of this, because when we talk about flavor in particle physics, this is what we mean. We're really talking about matter and the types of matter. So what even is this? So I'm going to give you a little bit of a historical picture as to how our picture of our human imagining of what it is that stuff is has evolved. I'll talk about the fundamental particles of matter as we understand them now, how we get from the stuff that we see in everyday life down to these little fundamental, as far as we know, point-like little things flying around. The fact that we have kinds of matter in the universe that are extremely short-lived, very ephemeral, that are still kinds of matter that can exist even if they're not surrounding us on a day-to-day basis, and the fact that these actually play a part in our understanding of how the universe evolved, how galaxies came to be, and so on. Yeah, what we can learn from studying these obscure types of non-daily life matter. So let's start with the stuff of daily life. So we have the block of wood. Maybe you say, I can see it, I can touch it, I can hold it in my hand, I can believe this stuff is something I might call matter. Of course, with air, that's something that I can feel when the wind blows. I can't see it necessarily. So we're already used to the idea that certain forms of matter might be more difficult to detect than other kinds of matter. They have different properties that would lead us to be more or less likely to understand what it is. But there's an awful lot of different kinds of things. So the question comes up, well, what makes up stuff? This is a question that's probably frankly been asked for tens of thousands of years, but at least here are some people who at least we remember having been in written traditions writing down ideas about the structure of matter, in particular that they came up with the idea that matter was made of lots of little things arranging themselves in some pattern. So at least as early as almost 3 millennia ago, people were asking the question, well, is there stuff, is matter maybe just made of little small things, which now we would call atoms. In fact, then in Greece they called atoms. So here are some people who thought about it, Canada and in India, modern India, Democritus and Epicurus in Greece, and Lucretius sort of following on in their steps in Rome. Now, there was a this is very much in the realm of philosophical discussion, and depending on who you ask, if you really want to say when were atoms really fully established as being a thing that exists, that's really something that only came about in the 20th century, basically through the work of Einstein and Jean Perrin. And these are still sort of roundabout arguments. And I include Perrin here because he's actually one of these sort of somewhat forgotten people who is actually the experimentalist who put sort of real tests to the picture that the theory of Einstein brought about. So if you really want to say who is really establishing this picture of atoms, you could almost say it's this guy. So let's show you a little bit here. So when we talk about the discovery of atoms, there's actually a phenomenon that was noticed a long time ago, which is sort of through line through to, in fact, the modern discovery of, establishment of atoms as a physical reality. So here's milk with the little globules of fat in it. And you'll notice that, and here's pigment particles in watercolor, and you'll notice that these little particles are jittering around a little bit of a random motion, right? So they're not sort of slowly and smoothly moving like they would in a current. They seem to be bouncing around in a sort of random way. So this is called Brownian motion today, although it was discovered long before Brown. In fact, there's a description of this in a poem by Lucretius. And to be honest, reading poetry about atoms is not the most, it's not the greatest experience for a modern day reader. But anyway, here's Lucretius describing the sun's light illuminating dust mites that are dancing around in the dark, and they're just moving, tumbling around and moving randomly. And he says, well, that's because they're being hit by viewless blows by these atoms. And the atoms are moving in whatever directions, and they hit these dust motes, and they go off in some random direction. So all the shifting movement is from the primeval atoms. Now, Einstein was able to write this down in math, and we're not going to explain what the math means, but in the end, this is the end of his paper that basically said, look, if this idea that this motion is coming from things being hit by atoms is correct, you should be able to determine a very specific number, and that from a combination of measurements and other things that were known. And if you would determine that number was consistent with all the other measurements of this number, that would say that this model was correct. And in fact, that's what Jean Perrin did, was to take this picture from the paper, do these measurements with all these little motes jumping about in different substances, and find that every time he got the correct value of n. And that really convinced people that this was a sensible model, and it was actually explaining what was going on. So this is not the only evidence for atoms, but it was sort of the thing that really convinced people that it wasn't just some sort of mathematical fiction that was used for chemistry, that these really were physical objects that were, they had some, they were very small, we couldn't see them with the naked eye, but they were bouncing around and hitting things and behaving like everyday objects. So that's indirect evidence for it. We didn't actually see atoms directly until, see in quotes, until the invention of a very special kind of microscope in the 1980s called a scanning tunneling microscope. And here's an example picture of one. So this is what a picture of a crystal looks like. So each of these blobs indicates an atom. And this is really, eventually they got to the point that they were spelling out the letters IBM with atoms. They got fancy pretty quickly. But this shows a chain that often happens in science, which is concerning from this hypothesis, there are atoms, we say this in the 8th century BC, and then coming up with indirect evidence for atoms, and which, people were, a lot of people were pretty convinced even before Perrin's observations that atoms were a thing. But then actually, even the Brown measurements are still kind of indirect evidence that, everything is consistent with this picture. And then finally, actually being able to directly probe them with some kind of detection apparatus. And this also illustrates the fact that we need to invent these special tools to look deeper into matter, that, sitting around and thinking about how matter must be, like the philosophers did, only gets you so far. And if you actually want to go take a peek, you have to go and build some instrumentation to take a look. So here we've gone from this block of matter to some atom. The atom's much smaller than this, obviously, we don't see it. So, okay, we have agreed that matter is made of atoms, but there's lots and lots of kinds of atoms, chemistry tells us. They combine in some way. So what was found, in fact, was to try and look into this picture of what are atoms really? Why do they come in certain types? Why are there certain elements? It was the first subatomic particle, which is the electron. which was discovered in a thing called cathode rays. Cosmic rays are a different thing. So cathode rays, where you can make this kind of weird little glass tube, and you wire them up to negative charge and positive charge terminals here. You make some very high voltage, and you turn off the lights. And what you find is that, in fact, this glass starts to glow, and there's a shadow they put in this cross here. This cross is apparently causing a shadow. So something is coming off of this end of the tube. It's going across the tube. Some of it hits it seems to be going in pretty straight lines because the shadow is pretty sharp. So some of it's getting absorbed here, and then some shows up on some's hitting the glass and then giving off a glow. And this is what, if you do various experiments, you can show that this must be much lighter than any atom. And this is somehow coming out of electricity. It's related with electricity. You can show it has negative charge. In fact, today, this is what we call the electron. This is a thing that moves when we have electricity. It's a thing that's flowing in the wires, hopping between atoms in order to do everything electric. So this was still in the 19th century when this was first found. And just as a sort of note here, this device here is really not that much different from the devices that until not so long ago were in many people's houses, cathode ray tubes and televisions. And these are really basically mass-produced electron accelerators. The electrons were produced here. They were liberated from atoms, accelerated by electric potential, and they hit the screen here, and where they glowed gave you a picture. So this weird fundamental physics gave us television. So here's a periodic table. This is a set of atoms that we know about, different kinds of elements, so including element 118. There's a whole bunch of things that are only made by people on Earth, but most of these are naturally occurring. And chemistry is telling us how these different elements, how these different kinds of atoms combine with each other. Now, we want to understand, somehow this has to be related to the structure of these atoms, we would say. And in fact, one of the great insights of quantum mechanics early in the 20th century was to understand that the electrons, which are a part of atoms, we can take them off atoms, we can put them back into atoms. They're basically orbiting around in atoms. These electrons arrange themselves. They have certain directions they like to go. They have certain shapes of the way they orbit, which are depicted, some of them, in this diagram here. And the way that the atoms combine with each other to make compounds, to make much bigger things that we know about, to make that wood. For example, if the electrons of one atom happen to like to distribute themselves like this, and the electrons of this other atom like to distribute themselves like that, then if they happen to be combining in a certain way, in fact, they'll attract these atoms to each other and sort of lock them together with an attraction here. So the world of chemistry is essentially the world of how electrons interact with each other. So the electrons are somehow in these atoms, and the electron arrangement and the way the electrons of adjacent atoms interact with each other give us chemistry as we know it. So the different elements in this table, in this periodic table, are determined by how many electrons that atom has. The number of electrons of that atom shapes the arrangement of these electrons, and those shapes determine what kinds of interactions those electrons have with other kinds of with other atoms. So the fact that carbon behaves in a certain way is because carbon has a certain number of electrons, and those electrons arrange themselves in a certain way, and that way happens to cause certain shapes to appear when, for example, multiple carbons are in a row. So, okay, we've got some number of electrons in atoms, but what determines how many electrons there are, and how are they orbiting? Here we have some picture that they have to be. There's some center here that something interesting must be happening there, right? So in fact, if you do an experiment, which was done by Geiger and Marsden, and this is indeed the Geiger of Geiger counters, in 1913, they found that by passing certain subatomic particles through atoms, through gold foil, in fact, sort of the depiction of the apparatus here. So here's the foil, and here's a little thing, here's a thing that people are staring at. They're actually counting how many particles are bouncing in various directions through these through the foil. Most of the particles they sent through went straight through, not very much bouncing around. Some deflected a little bit. Some basically seemed to bounce back. And if you think about it, if you have a sheet of Kleenex and you throw a bowling ball at it, you don't expect it to come back at you. So if it does, that really strongly suggests that it's hit something and has come back. So this really was very strong evidence that there was some very small and yet very massive core to atoms. And so in fact, most of the mass of an atom, 99.9% of it, is in a very tiny core, which is about a million billionth of the total volume of the atom. So it's a very, very, very small part. And in fact, if for another sort of scale picture here, the relationship between the size of U and the size of the nucleus of an atom is quite similar to the ratio between the size of the solar system and the size of U. So these are indeed very, very small things. And the electrons orbit around them, and there happen to be as much positive charge in the core as there is negative charge in the electrons around. So we call these the nucleus of the atom. The nuclei have a certain charge, and that attracts exactly enough electrons around it to neutralize that charge. So there are positively charged particles inside, which we call protons. And if you actually find how much these weigh, you find that they are more than just the protons. And in fact, that's explained by the fact that there are also neutrally charged particles with no charge, and they're called neutrons. So both of these were actually discovered independently. So we have this picture that the atoms are composed of some number of electrons that are orbiting a nucleus. And that nucleus has a certain number of protons, the same number of protons as electrons. And then these neutrons around in order to sort of fill out the thing. Because if you think about it, if you just had these positively charged protons, they would repel each other, and that would be make the nucleus unstable. So these neutrons kind of buffer them a little bit. Okay, so this will come back, and this is the most you'll see in terms of diagrams. So I'll explain what this is. In radioactivity, we find that contrary to the old picture that in fact, all the ancient atomists had, that atoms were immutable things, they didn't change, they were eternal. That in fact, elements can change into one another, atoms can change into another kind of atom. So one particular example is that if I take a neutron away from an atom, I just have a neutron that's sitting around, then it will eventually turn into a proton. Neutrons on their own are not stable. They will eventually turn into a proton, an electron, and something invisible, at least generally, which we today call an electron antineutrino, and that's a mouthful, but we'll come back to that. So here's a diagram depicting that. So we start off with a neutron, which we call N, and then as time flows along this horizontal direction, at some point we get a proton, which we call P, an electron, which I write E minus, here's the negative charge, and the electron antineutrino, which is nu sub E, but don't worry about it, it's just the third particle here. But the key message here is that one kind of matter can turn into a different kind. So this is called a decay. You can also combine two kinds of particles to make other kinds of particles. So there is a little bit of alchemy, you could say, that goes on here. In fact, if you were willing to throw away a lot of money, you could turn lead into gold. It turns out that's extremely difficult in practice. It's much easier to go the other way around. But anyway, this is transmutation that you can in fact do. And in fact, the sun is powered by a variant of this. So the sun is essentially a version where, in fact, you take a proton and you turn it into a neutron. So there was a wonderful theoretical paper that sort of explained this process. It was rejected by nature. In fact, it was a correct thing, which basically laid the groundwork for decades of research. And nature rejected it by saying it had speculations too remote from reality to be of interest to the readers. Not everything is accepted by nature. So I mentioned these neutrinos, or anti-neutrinos in that case. So in this particular decay, they were predicted to exist because the apparently energy would not have been conserved in that otherwise. And we really like the conservation of energy in physics. So we invented a new particle to explain it. And it turned out, if the fact that no one had seen them implied that they had to be extremely rarely interacting. In fact, if you do the computations, you find that almost all of them just pass through the Earth without stopping, without hitting anything. In fact, there's 100 trillion neutrinos passing through you every second. So there's a lot of them in the universe. They're not, I would say, everyday matter in the sense that we don't deal with them. But they are going, they are everywhere and they are going through you. So if you want to actually find them, this is a modern neutrino detector. It's called Super Kamiokande. It's a big tank. Here's people in a little float repairing parts of it. So these are essentially light detectors, and this is water. So when it's actually operational, the water is filled up here, and they look for little flashes of light that come when one of the very rare neutrinos that interacts in it does in fact hit a electron or one of the nuclei and causes a little flash of light. And then they can find that. So in fact, they can take a picture of the sun because the sun emits a lot of neutrinos. And so this is a picture of the sun. In fact, you can see the sun through the Earth, the sun is in fact there. So there are other kinds of detectors to try and find new particles, and this was a big cottage industry at a certain point in the 50s and 60s when new particles were at some level being discovered all the time, and people were trying to organize them into a coherent picture. So beyond this saying we have electrons and we've got nuclei, protons and neutrons, and we've got neutrinos, people found there are a lot of other random things going on. And so here's in fact, a picture from what was called a bubble chamber. So here's the bubble chamber is kind of hidden here. What it did, it really literally took photographs of bubbles that were being created by particles going through because they have charge. Here is someone actually reading one of these photographs and trying to decipher what particles were there. And this was, a definite skill to try and say, okay, well, here there's a little kink here, and then there's another kink, and then something invisible traveled a little while, and then something happened, and then these things we can see, but something invisible traveled from there. It's a whole big reconstruction job, and these were very, very skilled scanners, as they were called. So this enormous zoo of particles was assembled. Here is from the latest review of particle physics, which has a list of all the particles we know about of this kind. In fact, it goes off the page here. I couldn't show them all. So basically, there are a lot of things that had similarities to protons and neutrons, but people were struggling to fit them into some sort of coherent picture. And Enrico Fermi had a comment, one of these greats of the field, that if he could remember the names of these particles, he would have been a botanist. So there was a long search for an organizing principle that would allow us to collapse in the same way that we go from all the different kinds of chemical compounds, water, we can say, water is H2O. We were trying to find some way in which you could reduce this long list of particles to something more fundamental. And this was done by introducing things called quarks. So we have everyday substances. We say, all this matter is just combining atoms, different kinds of elements in a certain pattern. Then we've got all these different elements. Well, those elements are all formed by combining electrons, protons, and neutrons to make the atoms, and different numbers of protons and electrons and neutrons make different kinds of elements. then we say, well, we got lots of things that look like protons and neutrons in some way. Maybe we're combining more basic particles. We're going one level deeper again. And in fact, here's a set of explanations for a very small set of that list, where we have protons. If you actually work it out, you have to have 3 things inside, 3 quarks. Here, this one is called, protons would be up, up, down. Neutrons would be up, down, down. And then you could say, well, what if I had 3 ups or 3 downs? And that gives us particles, which are called deltas. Now, this is a little bit theoretical. Certainly when it was introduced, people didn't know if these were real things. In fact, maybe as a little aside, the name quark, which is sounds rather made up, is indeed made up. It comes from Joyce's Finnegan's Wake. So that to actually find a quark, you use a thing like this. So this is a very long particle accelerator. It still exists. It's located outside, just outside of Stanford. So there's a place where the electrons are produced and then accelerated. So they gain energy, kinetic energy, as they go down this pipe. And then there's a whole bunch of detection equipment in various places down here. So people would make experiments. And here's an experiment that in 1968 first saw evidence for quarks inside of protons. By showing that protons indeed were mushy, but had little hard cores inside. And it's basically a repeat of the gold foil experiment of Geiger and Marsden, where they fired something into gold foil and found that sometimes the particles came back. They found that if we fire electrons into protons, sometimes they come back. And that established the reality of these components of protons. So here's the picture. We start off with our everyday matter. We find that that's composed of atoms. The atoms are made of electrons and nuclei. The nuclei are made of protons and neutrons. And then we find the protons and neutrons themselves are made of quarks. And in fact, we call them up and down quarks because at that point we had run out of imagination. So all these wind up getting random English names, and you'll see more later. So we could say, well, is the picture down here? We have electrons, we have up and down quarks, we have neutrinos. We've never found anything inside quarks yet. So is that all? Well, the stuff we're made of is made of this stuff, but that's not the whole picture. So first, antimatter. So this is stuff that behaves exactly like our matter stuff behaves, except the charges are the other way around. So if I have, we have an electron, that's a familiar thing. The antiparticle of that is positively charged, and it's called a positron. And here's a picture of, in fact, I mean, these were discovered quite a while ago, of a positron going through, entering an experiment. Here is, I think, a lead plate, maybe copper, I don't know, it's some metal, and slowing down. And in fact, the fact that it curves more on this top side means that it's lost energy going through here. And you can tell that, in fact, it's positively charged if you do freshman E&M. You can tell that it's positively charged because of the direction that it's turning in this detector. So in fact, a long, long time ago, there was evidence that there were these weird particles that, in fact, they could show had the same mass as an electron, behaved otherwise exactly like electrons, except they were positively charged. Similarly, you can hunt for and find the antiparticle of the proton. We call these antiprotons. They are negatively charged, as one would expect, and they're made of antiquarks. So we have this sort of mirror version of the universe in which the particles that we know, the kind of matter that we know, have a corresponding kind of antimatter. And the very name here, to call it matter and antimatter, is sort of inherently privileging the idea of matter, because you say, well, antimatter is like matter, but opposite, right? Well, fundamentally, these things are actually very, they're very, very like each other, right? I could, in principle, be an antimatter being and say, well, but matter is the opposite of me, right? So they're not exactly the same, because we do look at the universe and we find that the stuff in the universe is matter. It's not antimatter. There aren't, as far as we know, and we've tried to find them, antimatter galaxies floating around somewhere. So we have this asymmetry. The reason we call it matter and the other stuff antimatter is because what remains in the universe today is matter. So there must be some small difference, assuming that you start off in the Big Bang with, symmetric universe, which most people do, then there has to be something that causes matter to win over antimatter in the end. So we think that there's some small difference between the two that favors matter. So there's antimatter, that's its own thing. Then there's other kinds of matter. So here's, again, something that was done a long time ago, in fact, by the same guy who found the positron, Carl Anderson, where you can look up in the sky, and this was understood for quite a while, that there are particles that come from space. In fact, they are protons mostly. And those protons hit the upper atmosphere and cause a bunch of nuclear reactions. And stuff, there's basically debris. Some of that debris has a long enough lifetime to hit the surface of the Earth. So these aren't electrons, protons, or neutrons. They're a new kind of particle called a muon. So like these. These are like electrons, except that they're 206, 207 times heavier. There was no, in fact, at the time, there was no conceptual picture for why these things should exist. And there was a famous comment from the physicist Arabi, who said, who ordered that sort of in the same way that you might at a restaurant, if you're ordering family style, suddenly wind up with a dish that you never really expected to get. So who knows? But there's some kind of thing here, behaves like an electron, has the same kind of charge as the electron. It basically has very similar kinds of fundamental theoretical properties, but is much heavier. So here's a picture.
Yeah, and I found cosmic rays. Cosmic rays? Yeah, there's this giant box called cloud chamber with a window in it. It's old, older than me, older than the observatory itself. Lots of little dials and switches. But the main part is that you look down into a window and
what do you see?
Well, if you're patient, you see evidence of cosmic rays that have traveled to Earth, exploding stars in our galaxy.
No way.
Yeah, they're all around us, everywhere. They're invisible and they travel right to everything, including us. But with this box, you can indirectly see the cosmic rays that are cloud-like lines they trace in the Earth.
How big are these cosmic rays?
Really small, subatomic. The cosmic rays, specifically these particles called muons, travel near the speed of light. But the cloud chamber captures their presence. It's like how fluttering leaves in a tree indirectly show us the presence of wind. Inside the cloud chamber, the air is supersaturated by a combination of evaporated alcohol and dry ice. When particles crash through the result of vapor, they create, through ionization, what looks like a cloud.
That is some serious science.
It's crazy. It's like the conjured magical world that gives you insight into our own world. There's actually more than just muons creating clouds. There's also electrons, positrons, alpha particles, but you've seen a cosmic ray with the cloud line with long streaks.
So that was a video from San Francisco's Exploratorium. And that showed, if you caught in the picture there, that in the video, that sometimes you did have these very long streaks, and those are characteristic of these muons coming from cosmic rays. And you also had a lot of short ones, and those short ones are generally actual natural radioactivity inside the box. There's a whole bunch of different things going on, but when this technology was developed, it was actually fairly clear that these kinds of extra particles existed. So we have this thing, the muon, that's kind of like a heavy electron. Turns out that there are heavy versions of the quarks as well, the up and down quarks. So here's one particular one, which I include because it's close to my heart, because this is, as was mentioned in the introduction, the kind of thing that I worked on when I was a grad student, although not on this experiment. This far predates me. But this is a picture of the so-called Mark I experiment at Stanford. It wasn't called that at the time because, it was called Mark I once they built Mark II. But this was in fact, sort of a predecessor of all kinds of modern particle physics collider experiments, so like the one I work on. And here is what's so-called event display. So here you can actually see the same kind of octagonal structure here. This is a schematic of a particular kind of a collision. In fact, this is a collision of an electron and its antimatter equivalent, the positron, in the middle of the detector. They make, they have a whole bunch of energy. They annihilate each other because that's matter and antimatter does that. And they turn into something new. The kinetic energy of their motion at the collision is turned into the mass energy of some new kind of particle, in this case, something called the psi prime. And that particle then decays. It is very short-lived. It turns into other things. And those other things that are long enough lived to see in the detector are then tracked. So each of these is a representation of an electronic signal that was seen in the detector. So unlike, in the past where you took photographs and you stared at the photographs, at this point we had gotten to using electronics and using computers to figure out what was going on. Now, the reason this particular display is kind of special is people used to say the particle is writing its own name in the event display. So this looks like a psi. So this is a modern event display. So this is from the experiment that I work on now, which is called Atlas. So this is an even heavier version. So the charm quark, that is the thing that is here, is the charm quark and the charm anti-quark are making this psi prime. This is the production of an even heavier version. So the charm is like a heavy version of the up, and the top is a heavy version of the charm. And so this is called, so this is a top. We produce it. It's very, very much heavier than charm. So this is something that was discovered only in 1995, not by us, but by a different experiment. But I show you our event display. And it has a specific pattern of what it turns into, the same way that here you have a specific pattern of things that you can look at and recognize that this came from a particular kind of parent particle. Here we have another specific pattern with an electron and a muon, and this other kind of quark, which is the heavy version of a down quark, which is called the bottom quark. And all these together in some pattern tell us that in fact we had produced a top quark which lived for a very, very short amount of time, 10 to the minus 25 seconds, and then turned into other things. So, in fact, we have a periodic table, just like we had a periodic table for atoms. There's a periodic table for quarks and the electron and the muon and the even heavier one called the tau. So it's simpler than the standard periodic table. There's only 3 columns. There's only 4 rows. Each of these columns is called a generation. So our standard matter consists of stuff in the first generation here. So our atoms are made of up and down quarks and electrons. But then we find there's a second generation. They have charm and something called strange. Okay, the names are very whimsical at this point for naming things. And then the muon. And then the third generation has the top and bottom quarks. People got less whimsical. And then the tau. So these are just getting progressively heavier as you go from left to right. And the properties, for example, the electric charge, in fact, all the charges are the same within each row. So the electron is negatively charged, so is the muon, so is the tau. There's also the neutrinos here. They're a little bit more complicated, so I don't discuss them too much, but there's also 3 kinds of neutrinos. They come in these families as well. And in fact, this one here, the so-called tau neutrino, the third generation, was the most recently discovered matter particle back in 2000. So you could ask, does this go on? Is there a fourth? We haven't seen one yet. Actually, there's pretty good evidence indirectly that there isn't one. So there's pretty good evidence. We know that there are 3 at least, and there's pretty good evidence that there's exactly 3. So I'm going to tell you what we can do with all this information, what we can learn about the nature of the universe other than just describe what's there. But let me give you a little bit of a big picture here first. So for the last half century, one might reasonably say that the theory of particle physics, explaining how all these different particles, how they interacted with each other, was one step ahead of experiment. So in a very real sense, once past this strange, these particles, past sort of a cutoff of 1965 or so, you could reasonably say that all of these were predicted at some level, or at least someone had an indication that they might be there. Whereas now, having found this one in 2000, this table is pretty much filled out. We don't have a reason to think that there's an equivalent fourth generation to look for. And in fact, there's another part of the picture which I didn't talk about, which is the forces between these particles. And that, in some sense, was completed with the discovery of the Higgs boson, you may have heard of, in 2012. So in a sense, we had a lot of vision as to where to go. We went and looked for things. And in fact, people were able, to predict 40 years or 50 years in advance what we would find. But once we found that, the question is, well, how does, where do we go from there? What's a bigger picture? And there's many great theoretical ideas, because we know that there are things we can't explain. And in fact, I'll tell you about them. But we need, in fact, now sort of the picture is the other way around. We need to actually find weirdnesses and use that to guide where theory should go, rather than having a theoretical picture and seeing if the world is consistent or not with it, I would say. So in a sense, we've got this, as well as a very good Swiss wayfinding if you're trying to go hiking in Switzerland. But we need a little bit of guidance as to which of these directions to head off for on the theoretical side. So we do have hints that this standard model, which is a standard model, as the name might suggest, isn't all there is to know. So what don't we understand and what are we trying to learn? So, I said, all the pictures I showed stopped with quarks and electrons. And, you might very well ask, are they made up of smaller things? So far, the answer is we've tried to do the same thing that we did to find nuclei in atoms, and then quarks inside protons, to look inside quarks and electrons. Haven't found anything. Why are matter and antimatter different? They have to be. And in fact, we know they are slightly. But are they, can we explain why there's matter in the universe and how much of it there is? Why exactly 3 generations? Why not 1? Why do we need more than 1? Why not 4? Are there differences beyond just the masses in these different generations? Where do the masses come from? As far as we know, these are just numbers that we can't explain. Other things, we have some kind of logical idea where they might have come from, other parameters, but the masses, as far as we know, they're just some numbers. Is this all there is? Is this the only kind of matter in the universe? So I'll tell you a little bit about my experiment. So I work at the Large Hadron Collider. So here's a aerial view so here's the city of Geneva, Switzerland, over here at the end of Lake Geneva, Mont Blanc in the background, the runway of Geneva Airport for scale here, and then this 17-mile circumference ring, which is the largest human-built accelerator on Earth. It makes the highest energy particle collisions ever made by humans. So protons are injected, they're accelerated both ways around the ring, and then they're collided. In fact, my experiment sits here, mine and 3,000 of my closest friends. There's only a few of these, so there's only one Large Hadron Collider. There's only one machine that can give you this kind of energy. There's only 4 major experiments at it. So the particle physics experimentalist community that works on this kind of stuff is very much coalesced around these particular experiments. So that collision energy is then turned into new particles through E = mc squared. If I have a lot of energy, I can turn it into mass. So this is actually 100 meters underground, which means that you can't get into it in most places. There's only a few elevators. And so if you want to get around the ring, you actually have to take a bicycle. So here's a folding bicycle on the Swiss-French border. So yeah, actually, I should mention, most of this is France, actually. Switzerland stops around here. So here's a picture of my experiment. There's actually not much of my experiment is in here. This is sort of the big superstructure. It's actually very hard to take a good photo of Atlas because most of the space is taken up by equipment, and so you can't actually get a good angle. So this is the photo we usually show, even if it's not great. It's showing all the parts of it. And this thing is actually about 8 stories tall. So here's a person in the structure. And here's a schematic of it, just to show again for scale. Here's people, and here's the size of the thing. And it is one of the bigger experiments in particle physics, although there's some that are much bigger. So that's all I'm going to talk about that. I'm now going to talk about some of the answers, or at least the methods we're using to probe these questions that I raised. So first, the difference between matter and antimatter. Again, we think that there has to be a difference between them in order to explain the fact that we have one and not the other now in the universe. And in fact, we know of a way in which they are different. It's represented by this very busy diagram, which I'm only going to explain to say, because I want to show it because this is one of the great achievements of, say, the last couple of decades of particle physics, really. I mean, this is a very impressive thing. But what it is it's showing, according to 2 different parameters. Again, don't care what the parameters are. They're just things you can measure, but you can measure them in different combinations by different experiments. So some experiments measure like this weird diagonal, some measure this, the size of this circle. And these different experiments are saying, well, some regions are consistent, some values of these parameters, some combinations are consistent with what we observe. So in this region, say this yellow measurement, it's consistent. The results of that experiment could be explained by a parameter here. It could be explained by a parameter here. It could be explained here. But in some places, maybe the yellow experiment says, okay, this is fine, but this blue experiment says, no, that's inconsistent with what we see. So you want to hunt for some spot in this diagram where all the different colors happen to sit on top of each other. Every experiment is consistent with that particular choice. And in fact, there is such a point. Now, if there hadn't been, if some of these had been inconsistent with each other, that would have told us that our picture was incomplete. We did not know going into this program of measurements that would be, that they all would agree up, but they actually do all agree in this particular corner. And the size of this triangle that's depicted here is actually a measurement of how different matter and antimatter are, at least how different quarks and antiquarks are. So they are different, but not different enough, unfortunately. So you can't, this is not enough to explain how the difference between matter and antimatter in the universe, at least as far as we know. Okay, maybe quarks don't do it. It turns out maybe neutrinos do it instead. So the same way that there can be differences between quarks and antiquarks, there can be differences between neutrinos and antineutrinos. And there's an experiment under construction called Dune, not to be confused with the book or the movie, which uses neutrinos being produced, in fact, in an accelerator facility near Chicago and being sent to South Dakota through the Earth, because again, remember, they go through stuff pretty easily, and in gigantic underground particle detector, which will hopefully be able to search for an equivalent kind of difference between neutrinos and antineutrinos that might be big enough to explain the difference between matter and antimatter in the universe. There's muon magnetism. So there are recent measurements of the magnetic behavior of the muon, pretty much literally what it does if you put it in a magnet. And in fact, these disagree with theoretical predictions. So there's a previous public lecture, which you can watch by Professor El Khadra from Illinois. And that's actually a very nice drill down into what's going on here. So this is the experiment that has recently done this measurement. And this is just a visualization of what was predicted with a theoretical uncertainty. So of course, we don't know exactly every single part of the prediction. It requires inputs that are a bit uncertain, so on. So there is an uncertainty in that, and you have to worry about that. And the experiment also has an uncertainty. So there's an uncertainty from two different measurements here. But when you average these results, you get this. And if the bands here overlapped with each other, we would say, okay, everything is consistent. The experimental measurements are consistent with the prediction, but they're not. They're actually very far apart. And in fact, they're so far apart that there has to be something. Pretty much everyone is convinced that something is going on. People are probably guessing it's not a problem with the experiment. The question is, is the prediction wrong in some way? Is it a prosaic wrongness? Is there a sign error? Probably not, but is it a prosaic kind of wrongness, or is there something new going on? Are muons different from our expectation? Because this expectation comes from thinking that they're just heavy electrons, basically. So similarly, there's this idea that electrons, muons, and taus are just different mass versions of each other. Essentially, it's called lepton universality, and there's other hints from other experiments that this might not be true. So you can compare the behavior of, say, electrons and muons, or muons and taus, in various interactions here. Well, maybe you start off with a B quark, and then you wind up with a strange and electrons or muons. Or you start with a B quark, you wind up with a charm quark, neutrinos, and muon or tau. And if you compare these, so you would expect that if electrons or muons are just like each other, then the rate at which it turns into electrons or it turns into muons ought to be the same. So this is a particular, we call it RK because we do. But you expect that the value should be 1. It's been measured recently by an experiment to be pretty, not at standards of that we would claim a discovery yet, but pretty suggestively, these error bars do not include the value 1. And so this is a very tantalizing hint that maybe electrons and muons don't behave quite the same way. Similarly, you can do this with mu and tau. And so here it's not 1 because actually the mass of the tau matters here, but this is what the prediction would be. And this is in fact the current average. So this is these are two quantities, and you measure these quantities together. So this is a prediction of what you would be on these two quantities, and this red region doesn't overlap that. And again, maybe this is a hint that muons and taus aren't quite behaving the same way. So this, if we actually were able to confirm this kind of behavior in the future, this will be really fascinating, because that will be the first real demonstration that in fact the generations aren't just, there's something fundamentally different about each generation, and that can give us a hint. Dark matter, this is a completely different topic, and I won't go into it in detail, but in fact, I'm very chauvinistic in talking about our kind of matter, because if you do studies of cosmology, you look at the behavior of the universe, in fact, even at the level of our galaxy, you can infer from gravitational behavior that, in fact, the vast majority of matter in the universe is not our kind of matter. Our kind of matter makes up about 5% of the total energy budget. Over 5 times that is something else called dark matter. It's called dark matter because we can't see it except through gravity, and it's not something that we know. We don't even know if it interacts with our kind of matter at all. Here's actually a picture which is formed from comparing. So these clusters these are clusters of galaxies that have moved through each other. And the gas in these clusters of galaxies is essentially smashed into each other, is slowed down. You can actually see the bow shock here. And so it's slowed down. But if you use a technique called gravitational lensing to figure out where all the mass of these clusters is, you find that it's in this blue region. In fact, it's overshot. So we see that, in fact, the matter, and actually the galaxies, because the galaxies themselves don't really collide, it's the gas between the galaxies that's colliding here. So that, in fact, the mass has separated itself from the actual collision here. In fact, we know that of the visible matter in these clusters that most of it is in fact in gas. So somehow there's some kind of matter that is overshot where the visible matter is. And it's not, there's a whole bunch of things that come together to convince us that dark matter exists. In particular, without dark matter, we don't really know how to make galaxies form if you're trying to simulate the evolution of the universe after the Big Bang. So the fact that we're here to talk about the nature of the universe is at least partially because of the fact that this kind of dark matter exists. And I didn't comment on it here, but I might as well do so. The fact that you can actually have this kind of triangle at all, that there is a difference between matter and antimatter through this particular mechanism, comes from you have to have at least 3 generations of particles. So if you don't have 3 generations of particles, there may be other ways of making a matter-antimatter difference, but this particular mechanism, which may be verified by this neutrino experiment, wouldn't work. So it could be that to form our galaxy, you need dark matter, which is some kind of thing we don't really know what it is yet. And to have a matter-antimatter difference for our kind of matter, you need 3 generations. So there's a lot really to understand as to the fundamental, how these different kinds of matter fit into a bigger picture. So in summary, here's our picture of the fundamental constituents, at least of our kind of matter. On top of this, we have the antimatter equivalents of them. And then, in fact, most of the matter in the universe is something that's not in this table, but we are, working very hard to try and understand what that is. And we think that, in fact, even though our regular matter is only made up of a few things in this, that the other kinds of the fact that you have 3 generations, for example, may be necessary for us to wind up with the kind of universe that we have today. The fact that you have this other kind of dark matter that we don't know what it is, maybe we do believe is necessary to wind up with the galactic structures that we have today. So in fact, these kinds of matter, even if they don't exist, they're not something that we interact with in everyday life, it may be utterly critical to the fact that we're here at all to talk about them. So this is really why we continue to study these kinds of weird, obscure particles as much as we can, and we very much appreciate the fact that everyone else seems to think that these are exciting to learn about too, and because we everything we do is with public support and public funding. So this is as much everyone's particle discoveries as they are ours. So. And I will just end with a picture of wildflowers in Texas, because I like to do that. So. All right, so that's all I had.
Thank you. So thank you, Peter, for this very nice talk. We have a couple of questions in the chat. Maybe you could answer those, and then we'll move to the
Okay.
other questions.
I have to find the chat. Okay. All right, so we've been taught since day one not to think of the electron as a BB whirling around a nucleus, that it's really a diffuse energy blob. Okay, how do we see the electron trail in the cloud chambers of point-shaped particles? So this is a great question, and actually, it's one of the. It's still a mental picture issue that I have today. So the way to think of it is that the location of the electron, so quantum mechanics says that the location of the electron is a very is generally a not precisely determined thing until you actually go and look, right? So you shouldn't think of it as the electron is literally in a place whirling around the nucleus, but it's actually in a single location at some time. And generally, if you're not actually measuring where it is, could be anywhere. There's some probability of where it is. But if you do an experiment that specifically tries to knock the electron out or something, or let's say a quark, right? When you're doing an experiment to find a quark inside a proton, it actually does localize the electron. So the electron, as far as we know, if you do experiments that ask what is the size of the electron itself, you find that the electron is as far as we know, a point, an infinitesimally small thing. But it does, but when you're not like doing that, the electron is sort of spread out. and it could be in a lot of places, but the actual size of the electron, as far as we know, is a point.
I make a statement on that?
Sure.
So my question really is, when I see the very point of the electron in the cloud chamber, it is a point, it is a BB, and it is doing something, and it is whirling around something or being affected by a magnetic field. Why can't we then just consider the electron as a point instead of a smear?
Well, because you're doing a different kind of measurement. So, I mean, it's not wrong. I mean, an electron is a discrete thing. You can get a single electron in a box, and you can fire the electron somewhere. You can measure where that electron is. But when the electron is, this is getting into quantum mechanics, and it's a long story maybe. But if you are doing, if the electron is in orbit in an atom, the electron is not, you're not doing the measurement of where is it all the time. And so quantum mechanics says, well, there's, a different sort of property of it emerges. And that property is one where it's kind of smeared out in this, the location of it anyway, smeared out in a certain shape. So it's really coming down to the quantum mechanics saying you're doing different kinds of things. And so the way the observational behavior of it is different. But it's really a quantum mechanical question.
So we have a question from Barbara. Can you?
We do?
Yeah.
Raised hand?
Mm-hmm. Right.
Go ahead.
Yeah.
In the very early stages of the universe, before the condensation of hadrons, the universe, I guess, consisted primarily of quarks. And I want to know if all the quarks that you have described were in existence at that point, and whether the asymmetry between matter and antimatter existed at that point, and whether the quarks have any role in inflation.
Okay, great question. So yes, at the time that the hadrons form, the belief is that, at least by, for example, the model that which would involve neutrinos, that the asymmetry between matter and antimatter is already baked in at that point. So that happens at a very, very early stage. So by the time you get around to the quarks forming hadrons, that's already frozen in. Exactly what causes inflation is still a very, very open question, and yeah, I'm not going to say anything about that.
Okay, so we had a question from Connor.
Hi there. Very nice talk. Thank you. I have a couple questions. One, is there such thing as an anti-atom, or is it just anti-particles?
Yes, there are. People were, I mean, not super recently, but I mean, it has been made. So you can make anti-hydrogen. So you make an antiproton and you make a positron. You put them in orbit around each other. It's exponentially harder to make heavier anti-atoms, because then you have to assemble all this stuff, and it's not easy. It's probably not going to get very many more anti-atoms than that. Now, of course, there have also been anti-nuclei detected from space. I mean, when I say that there is no antimatter up there, that's not completely true. There is a little bit, but we think that it's actually sort of made through high energy collisions in the universe, and so it's not remnant from the beginning. It's fairly recently created, but there is like anti-helium that you can find.
Okay, gotcha. And then what happens when two unlike particles meet? So like if a proton were to meet a positron, is that different?
Yeah, nothing in particular.
So it would just act like, go ahead.
Yeah, I mean, like nothing more than what would happen if a proton met an electron. I mean, they would attract or repel each other electrically, but it's not. Yeah, they would not annihilate. The annihilation, in fact, even the annihilation I think one sometimes gets the picture that, you know, the antimatter and the matter search for each other and then, like, you know, kill each other as quickly as they can. And in fact, you can have a positron and an electron orbit each other for quite a while. In fact, we study this kind of orbiting system, and you know, you actually learn very interesting things from it. So, you know, they can, you know, they can sort of dance around each other for a while before the annihilation happens. But there are also studies, you know, where you take, say, a muon and a positively charged muon and an electron, they'll orbit each other, but they don't annihilate each other.
Gotcha. And then one last quick one. How do you work with antimatter without annihilating it? Do you just use the other particles?
You try to be very careful to not let it touch anything. So you need really good vacuums. You generally don't store it, right? You generally basically make it and then use it as quickly as you can. So in the Large Hadron, well, in fact, that's part of the reason, you know, that the Large Hadron Collider collides protons in both directions and not antiprotons. Like a previous accelerator used antiprotons, but it's really hard to make antiprotons, it turns out. And it's certainly hard to store them. So in general, what you do is you have really good vacuums. You just try and, you know, not let it run into anything. You suspend it with magnetic fields, basically, and eventually you just accept that it's going to leak out and annihilate.
Great, thank you.
Okay, and we have a question from Charlie.
From the chat, right?
And also on the screen.
Oh, wait, was this the same question from the chat then?
Yeah, basically, I posted an article from Quantum Magazine from 2016 that claimed that the lack of discovery of any new fundamental particles was a problem for physics. And like I said, this was 2016, so I don't know if things have changed in that time. But is there some reason why there should be a small list of fundamental particles? Theoretically, or are there theoretical arguments that would argue that there should not be a small finite list of fundamental particles? And you know, that kind of, you know, what's going on there, you know, I don't know if you're aware of that article or not, but it's, you know, because of the particle zoo back in the 70s, there was this kind of idea that this was going to be a never-ending cornucopia of you know, that there would not be a finite list of fundamental particles, that they would just go on forever, and but that doesn't seem to be the case at the present time. Is that article relevant today or not? Or anyway, that's the question.
So I haven't read that particular article. But I can guess at the sort of general thing, so the general thrust of it. So maybe I'll say a little bit about that. So actually, you know, the funny thing is that, you know, we talk about the particle zoo. I showed that table from the particle data group. In fact, most of those were discovered after quarks were discovered. So even at the point where quarks were used to sort of organize all the things that were known into a sort of coherent picture, we kept finding more kinds of things that were made of quarks. So in fact, you know, my experiments found one. Our sister experiment, LHCb, also the Large Hadron Collider, has found quite a few. And those are actually important because you're studying how the quarks orbit each other, basically, and that actually tells you about the forces between them. And you know, I didn't really talk about this, but you know, we spend a lot of time breaking things down to very small, finer and finer scales. But you also want to understand how you build up from those scales, right? Like I can't just say, oh, chemistry is solved because, you know, obviously we can do quantum mechanics and physics, so therefore no chemistry, right? Like there's an awful lot to do to figure out how you go from the basic bits back up. So that's one thing. But in terms of the sort of issue of no new fundamental particles, I think this comes back, okay, this is a very personal view of it, but I think I'm allowed to do that. It comes down to a question of what exactly are you expecting, and is that, you know, is that really related to what nature's doing, right? So, you know, I'm an experimentalist. I try not to project my own personal opinions about how nature ought to be onto nature. And so in a sense, finding new fundamental particles tells us that there's some kind of new force, or there's some kind of new kind of matter, and it, potentially unlocks some kind of explanations, or if you're looking for directions to go to try and guide theoretical research, then that's exactly the sort of thing that you want, because that tells you, okay, you need to explain this thing that we have not been able to explain yet. And in a very real sense, dark matter is that, right? We think the most likely explanation is that dark matter is some kind of particle that we don't know what it is. So people really are looking to try and see if they can find it, either make it in the lab or detect the dark matter that that's existing around, and try and understand some of its properties, because that gives a direction for people to be able to search. In terms of our kind of matter, or are the forces that govern us, actually, I mean, I have a whole spiel on this, but in fact, there's not seeing anything is in fact in contradiction to a lot of expectations. But from a scientific point of view, the fact that a lot of expectations that were had going into the Large Hadron Collider have been contradicted is as fascinating as if we just confirmed any of them, right? So it's almost more interesting for everyone to have been wrong, rather than for everyone except two people to have been wrong. So I think it's really actually a very interesting opportunity. It gives us much more of a sort of big question mark as to where we go from here. But I think it's an interesting place to be in science, to actually not know what the immediate next thing is, rather than having someone already 50 years ago tell you, well, it's probably X, and then going finding X.
So there's no theoretical reason to expect that you would end your quest with a small finite list.
There's theoretical reasons to expect. I mean, again, the theory is at some level describing what's actually there, right? So, you don't expect the list to be infinite unless something kind of weird is going on. But why did it have to be 3 generations and not 4? No one has an answer for that. So.
Okay, so we have another question in the chat by Peter. I'm sorry, by John. Any progress on the neutron decay time, beam versus bottle discrepancy?
So this I actually can't really give an answer for, because that's not really my field. But sorry.
Okay, and maybe we'll just take one other question by Connor.
Hi, yes. Something you said that you detected antimatter from space. How do you determine antimatter from matter in space?
So more or less the same way you do it on the ground. So let me get the positron picture again. Ugh.
So you were at the exploratory today, huh?
I do not want
Yeah, and I
to
found
see that again. Great as that video is. Okay. Okay. So right. So here's the logic to say that this thing is positively charged and actually, like an electron. So you have a magnetic field here. So that tells you that this thing, if it bends left, it's positively charged, and if it bends right, it's negatively charged. So this thing is positively charged. You can tell that it's going from bottom to top because it's going much straighter, and then it loses energy, and then it slows down and starts to bend more. So that tells you, that's turning left and positively charged. And the amount of that by which it slows down is related to how massive it is. So if it were muon, actually it would be slowing down less than it does. And so this can give you a hint as to the mass of the thing. So if you go out, and we have much more powerful techniques to do that measurement now, but basically if you go out and you look for something that is functionally, like massively, the mass is the same as a proton or a helium nucleus or something, but it bends the wrong way in a magnetic field. In fact, they basically have these gigantic permanent magnets in this particular experiment, which bend the particle trajectories. Then you can say, well, actually, it must be antimatter because it has the wrong charge.
Okay, so thank you very much, Peter, for this wonderful talk, and thanks for joining everyone. And if you're curious about dark matter, you can join next week's lecture by Catherine Fries on dark matter. Okay, thank you.
All right. Thanks everyone for connecting.